The following is the video solution from JSDT Solutions. Question 7 says, in the diagram below, AC and CE are tangents to the circle with center O. B, D, G, and H are points on the circumference of the circle. HG is produced to F, and then we have BD is equal to BH. Okay, so we have a nice isosceles triangle over here, and they tell us that angle D1 is X, and angle D4 is also X because they are equal. Okay, so the first question is to find 4 other angles equal to X. 4 other angles. Okay, let's see. So we already know we are at a big advantage here because we have this tangent. So, and it's a tangent you see on both sides. So if this is a tangent over here, we can just use the tan chord theorem. Here's the angle between the tangent and the chord. So it's equal to the angle at the circumference subtended by that same chord. So this is X as well. Okay, so we know that is X. And we can go ahead and put that down. We can tell them that angle H1 is equal to X because of the tan chord theorem. Okay, which other angle would be equal to X here? Let's just capture all the, tangent ones. So here we also have an angle between the tangent and a chord. So it's going to be equal to the angle in this circle at the circumference supported by that same chord. So this is also X. Angle H2 is also equal to X. So we can tell them angle H2 is equal to X as well for the same reason. Okay, and then what else do we have? Well, let's just focus on the things that they told us, the special things. We've used the tangents, okay? There's no angle on this side, so we can't really use that tangent. But they did tell us that BD and BH were equal. Since those lines are equal, we have an isosceles triangle here. And then that would mean that the angles opposite their equal sides would be equal. So if this is X, this is also X. So we can see that angle D2 is equal to X because of angles opposite equal sides are equal. So angle D2 equals X, and put our reason. And which other one do we have? Okay, we have an isosceles triangle here, but you see how we have tangents. This is CB and this is CD. So tangents drawn from the same point to the circle are equal. So CB is equal to CD, okay? From that common point to where they touch the circle, they would be equal. So since these are equal, and with this you have to actually state that. You see that? I didn't really need to state that because they already told us that. So start by telling them CB is equal to CD. So CB equals CD. And because that is because of tangents shown from the same point to a circle are equal. And then the conclusion there with the angles would mean that the angles opposite their equal sides would be equal. So this is also X because that is X. Okay, angles opposite their equal sides. So angle B3 is also equal to X. Angle B3 is equal to X because of angles opposite equal sides are equal. And there we go. Okay, those are 4 angles equal to X. We have made sure to also put those down. I'll leave these lines here just in case we need them. Let's just leave them all in the same color so we know, everything that related to X. And that is our answer. Moving on to the next question. And then question 7.2 says, hence or otherwise, prove that BD is parallel to HG. So HG and BD, let's see those. Okay, so this is BD, this is HG. Why are they parallel? Well, if we can think about theorems that refer to parallel lines. If we can find that any of those theorems are true, then these lines are parallel. So we can work with fun angles here. And straight away, I see that if we join DH, we have formed alternate angles. Okay, this is a Z. So you see how this angle is already equal to this angle? They're both equal to X. So we can go ahead and tell them that we can see alternate angles here. Since they are equal, the lines are parallel. So we can tell them D2 equals H2. So angle D2 is equal to angle H2, and they're both equal to X. Therefore, BD is indeed parallel to HG. And this is because the alternate angles are equal. Therefore, the lines are parallel. So I'm also just going to put down, parallel just to show that these lines are parallel as well. Okay, moving on to the next question. Question 7.3 says, show that angle G2 is equal to 180 degrees minus 2x. So this is angle G2. Why would this be equal to 180 degrees minus 2x? Well, they use 180 degrees, so clearly they are making it refer to this straight line. Angles on a straight line add up to 180 degrees. So it's probably that angle G1 is equal to 2x. So then to find G2, you said 180 degrees minus 2x would give you angle G2. Okay, so why would this possibly be equal to 2x? Okay, so I'm looking at this, and after looking at this, I just realized that I can't really see angle G1 immediately being equal to 2x. But I do see this, okay, because I was looking for an exterior angle in this triangle, and, this is already an interior angle. So, yeah, this can't be the exterior angle including this. But if you look at it like this, so just go ahead and look at the shape, right? You see that we have a cyclic chord here, and then this is the exterior angle. Angle G2 is the exterior angle. If this is the exterior angle of the cyclic chord, it is equal to the opposite interior angle. So it has something to do with angle B2. If you find angle B2, then you'll know what G2 is. And this is the one that is 180 degrees minus 2x. So our goal is to find angle B2. Okay, so it's a usual story with Euclid and how you jump from one thing to another thing. To find this, you must find this, and so on. So how do we find angle B2? Well, angle B2 can be found if we know what B1 is. How do we find B1? Angle B1 is between a tangent and a chord. So it's equal to the angle at the circumference supported by the same chord BH, okay? Subtended by the same chord. So that would be angle D2. So that is equal to x. So that's where we start. We'll tell them that angle B1 first. Angle B1 is equal to x because of the tan chord theorem. And then from angle B1, we can find angle B2. So angle B2 will be found by saying this is a straight line. So the angles on the straight line add up to 180 degrees. So angle B2 will be found by saying 180 degrees minus that x minus the other x that we have, those two x's there. And then this is angles on a straight line, the sum of angles on a straight line. Okay, so angle B2 is equal to 180 degrees minus 2x. And then finally, to find this angle G2, you see that angle G2 and angle B2, okay, they're equal because this is the exterior angle of the cyclic chord, so it's equal to the opposite interior angle. So finally, angle G2 is equal to angle B2. Therefore, it's equal to 180 degrees minus 2x because of the exterior angle of a cyclic chord. Okay, and there we go. We've proven that. Now, this took 3 steps. This was for 2 marks, so there was probably a quicker method. And let me see, what would have been the quicker alternative? Okay, so here is the alternative method that we could have used. You see how this is a tangent and this is a chord. And so the angle between the tangent and the chord D1 and D2, okay, which make up 2x, they would be equal to the angle at the circumference subtended by that same chord. So this would also be 2x. Therefore, angles on a straight line add up to 180 degrees, and this would still be 180 degrees minus 2x. Okay, so yeah, 2 ways that you could have done that. That would have been quicker. But there we go. That is our answer. And that is the last question for question 7. And that is it for question 7.